right, let's see if that works. Yep, that worked. The shortcut worked. All right, anyways, hello everyone. Let me post this into a few places. I don't have a bot for this yet. And then you should let me know if you are hearing me. Anyways, hello and welcome to my little stream here. I decided that I will try to document the process of developing a PCB, basically from scratch, although it is based on something that was copied already a bajillion times. So what am I talking about? Just recently a friend of mine, Uwe Hermann, from the project Sigrok, sent me some boards to look over for his tiny logic analyzer that is just 13 by 13 millimeter size. And I decided that it would be fun to make my own addition to that collection, also an open hardware device that is also based on the fx2 microcontroller with the USB interface. And I would like to try to document that process of putting that together. It will be hopefully relatively small project that we will be able to do together. Anyways, let me give you some background for this. Let me see, because I'm still also figuring out all the streaming situation here. So I'm testing my buttons here. So that's the desktop. There you go. I hope this is actually coming through. And let me just really quickly check that the stream health is good. It seems that it is the case. And there are some people watching. That's nice. And also I have created a Gitter chat. Oh. Hey, Azadron, that is nice that people from Micah's channel are coming over. It is really cool to have some of you guys come over and check out what I'm showing here too. I hope the audio is good, so let me know that if this is the right levels, because it's all a new setup. All right. Let me check once again. Yeah, okay, I have the overlay version. So what we will be working on is an addition to the fx2grok interface. And this is a USB to GPIO input device, basically. It's very simple. It streams the data from a GPIO port. And the nice thing about the FX2 is that there is a lot of internal hardware inside of the device that speeds this up. So you probably have seen, and let me show that. You've probably seen the Salia Logic. It's a very awesome device. They have also very cool software, but it is closed source, closed hardware. So Sigrok is a nice alternative to that. With that, we can have a completely open source toolchain and open source devices for it. There are some very cheap Chinese clones of this, a lot of them, like a lot. And I still don't see my monitoring video because YouTube is being difficult. But anyways, okay, should work now. There you go. That's upside down. Okay, there you go. So that's Logic, and they're clones. This one I renamed to Sigrok because that's what I bought it for, not rip off someone who put a lot of effort into their software and hardware. Anyways, so if we look on the website, here is the Wiki page, and this is the project that Uwe created. It's this 13 by 13 millimeter PCB But what we want to do is something a little bit bigger, a little bit easier to assemble, and see where it goes. And that's why the project is for now called fx2grok flat. Then on the same website, you will be able to find the documentation for it, also the data sheets for all the parts. There is also the complete bill of materials to put one of the 13mm boards together. And the project that Uwe started very long time ago. He started it, I think, 3 years ago, and he only recently sent me a message that he's done with it. So we ordered a few prototype boards. We have a schematic for that I took over, but okay, let me close here. We have too much stuff open. There we go. So there is the schematic of the flat copy. And the problem is this is so old that the KiCad files are probably contain some really old legacy stuff in it. So we will really start from scratch. I will copy most of the schematic, but we will be adding some additional things that are not on the 13mm version, like an EEPROM, so that we can store the VID and PID for the microcontroller, so it can show itself to Sigrok and be detected correctly as a device for Sigrok to be used as a logic analyzer. We will be adding input protection that is missing here, and mainly some diodes to do clamping of the input, as well as a few resistors, so that the whole thing is a little bit safer. If we do anything else, I don't know. Mostly I want to stay with the micro USB connector. I use it a lot and I like it. I think it is a reasonably robust solution. And that's pretty much it. So the first thing would be to probably start a new. This is the hardware repository. I tend to keep the hardware designs inside Git, and we will go to fx2grok flat, and we will basically start a new directory. Let's call it, because this was, first of all, I copied the 13mm version of the schematic, and we will start from scratch. So let's make a new directory. It's 0.2 whatever, 0.2. And yeah, so here we will close this and start a new project. I rarely start new projects in KiCad. I usually copy something that I already used before. So let's go here, flat 0.2, and call it fx2grok flat, and save. And then we have a schematic. The first thing would be to add some information like 0.2, title fx2grok flat, and the rest we can fill in later. I usually put it as copyright of mine, and we will make it under Creative Commons by attribution, share alike version 4.0. So that's the licensing that I tend to use for my hardware. Okay, so I printed out the old schematic so that I have something to go from, like here, and we will be able to copy that. So let's just drop in this stuff. First of all, we have to in this component libraries, we have to add the schematic libraries that I tend to use. That would be, first we need the path for it, and that would be projects, Sigrok, we have a lot of stuff, Sigrok, and then library, pretty KiCad libs, this is the stuff that I use. and relative path, and then it does this. I don't know why KiCad does this, where it creates this really massive path going from home, but we will be able to clean this up. So let me clean this up. Let's close this, save and exit, and go into here and just edit it in the text editor. Just a little bit dumb, but this is what it is. Flat.project, I think. Yes, there we go. So the libdir and I think it will be 2 layers up, 3, and then libpkl. Yeah, because it is hardware fx2grok. Yeah, that should work. Okay, let's do this. Let's reopen this. Let's just close that completely and open KiCad again, just in case KiCad is being dumb for some reason. We don't know. Okay. Preferences, component libraries, and this is gone. Great. Why did it disappear? Probably it overwrote it. Let's see. Is it gone? Oh, home libpkl. Ah, there we go. That should be better. Let's see if that works. Yeah, I'm not sure this overlay of the keys on the screen is that useful. I added this in case people are asking themselves what keyboard shortcuts I'm using, and I thought that might be useful. Okay, so let's close this again. Let's close this again and see if this detected it. Preferences, component libraries. Yeah, there we go. The reference path is in here. So now we can add this and go into projects, Sigrok. Yeah, library pkl. There we go. So now we have schematic libraries. I have a bunch of them. I just add them all. Okay, so let's add the fx2 from pkl Cypress. There's only one symbol at the moment. So that is our center of attention. And let's add just that. Then let's add the USB connector and pkl connectors probably. USB, pkl, USB, OTG. There you go. Let's flip it around. Edit component. Component there, mirror. Why? Yeah. Hey, microhex. Live KiCad action. That's exactly right. Oh, yeah, good. That should be part of, yeah, I see also the chat on Micah's live chat. So, yeah, guys, I'm trying to make it also a little bit of an intro while I'm working on this. Okay, so we have a USB connector. Then we need a few more things. Let's drop in a capacitor. Although it would be probably useful, yeah, for the especially for the capacitors and resistors, it is good to, when you drop in the first symbol, is to already set the footprint for it. Just so when you copy it, you don't have to assign them later, but yeah, we'll show you in a sec. Capacitor small. Let's edit this. Let's add a footprint while we are already at it. And this is dipole capacitor 0402. There we go. Assigned. Oh, yes, yes, yes. It's always showing it. Let's hide it. Okay, we have a capacitor, then let's drop in a resistor, device, resistor, QR, R small, R small. Yeah, I tend to use the small symbols. I don't know, I just prefer, in general, I like to make things small, so probably that's why I also use small symbols. Sign footprint, and then resistor 0402. There we go. Yes, and disable this. All right, there we go. Now, what else do we need? Looking at the schematic of the old guy. Yeah, we will need a crystal and so on and so forth. Yeah, let's just add some of the signals for that are here. So the design rule for KiCad that I read somewhere a long time ago is to use the secondary grid as your alignment. I should probably just set everything. So they're saying, let's see, okay, grid. If you go on grid size, the default grid size is 50 mil, so half an inch, yeah. And yes, 50 mils is 1/20th of an inch, right? So this is 1/10 and this is 1/20th. So they are usually saying to use 1/10 as an alignment, but for some reason the default of the grid is set too much larger. And now I cannot delete this stuff because it is not aligned with the grid. So I will delete the old grid stuff and then set it to delete the junctions and move this stuff, move it and align it with this grid. Then yeah, it's some design rule that I read a long time ago, and I tend to hold on to it for no particular reason, but I do. There we go. Okay, now let's add those traces. Okay, this will be attached to 3.3 volts. So let's drop in the power symbol for that. Power 3v3. Bam. So what library I will be using for the parts? So I don't use the off-the-shelf libraries very much from KiCad. There are some librarians that are making a really good job, but they also tend to swap out parts without my knowledge. And it happened already in the past where, for example, diodes turned the orientation. So suddenly I opened a schematic and all the diodes were reversed without any announcement or anything. So I don't tend to use the off-the-shelf libraries. All I do is maintain pretty KiCad libs that I made. It's on my GitHub. It's under Esden-Tempski-KiCad-libs. And this is what I use most of the time. And then I copy, if there is a symbol or a footprint that is decent in the generic libraries, I copy it over. Sometimes do some changes, sometimes not, but I copy it over and keep it in my library. The reason is, then I have it as a submodule of my hardware design, making it static. It will not change suddenly. It will only change if I specifically update those libraries. That is in general not that big of a deal anyways, because by now KiCad is actually checking against the libraries what it has stored within the project. So if you have a project, all the symbols and all the footprints are inside the project files. And then it compares to the libraries that are installed on your system. So then you get a pop-up if the stuff on the hard disk changed versus the stuff that you have in your project, and it asks you if you want to rescue the symbols that you used, or if it should just use the ones that are in the library and update it nonetheless. So it's not that big of an issue, but just historically I had that experience that these things happen, so I started maintaining my own library. Also, some of the designs, like symbols, I have a little bit different style to the designers of the libraries that come with KiCad, so I tend to maintain this. If you ask a bunch of hardware designers that use even the expensive packages like Altium or OrCAD, they all will tell you that they usually maintain their own libraries for footprints and symbols, because half of the design of a board ends up being drawing new symbols and drawing new footprints anyways, and they like to have the full control over what they are using and not use someone else's library that they have no idea what it will be about, and what changes and what design rules they used, and so on and so forth. So most people tend to maintain their own set of libraries. I think using a submodule in Git is also a good way of keeping that up to date with your project, so it's not that big of a deal. I hope that answers your question, Microhex. All right, so let's get back to the copying of that schematic. So we had a bunch of stuff that was unconnected. We didn't need the ready, we didn't need the second ready. I still have to read more of the datasheet of the chip. There's some stuff that I still don't exactly know about. I tried to prepare myself for the stream by reading as much as I could, or the most relevant stuff. But I don't have too much experience with the particular chip yet. So there is a clock out and IF clock that I will have to check what that exactly is. Then we have several GPIO banks. We will only be using the middle bank for the 8 digital inputs, which is funny because you can actually use them as outputs. So you can use the fx2 based logic analyzers as signal generators, at least for square wave outputs. So that's quite a useful thing. Someone made a firmware for that to convert the fx2 based logic analyzers into square wave signal generators. It's quite a useful tool. And let's disable these. So in KiCad, compared to the software package with the bird, you didn't have to mark IOs that you didn't use as not connected. In KiCad it is, and in many other more prominent commercial packages, you have to mark them explicitly because you want to make sure that you didn't by accident leave something unconnected. So you mark stuff that you don't want connected explicitly, that you don't have a connection there. So you use the non-connect tool for that. Okay, so next thing will be the PA0. This is for the LED. So this is the output for the LED for the status. PA0. PA0, and then we want to get the outputs. And this will be PB0 to 7. Yeah, the nice thing in KiCad is compared to Eagle that I used in the past, that you can use just arrow keys on the keyboard to navigate the mouse. They might have added it in the meantime. It's like I didn't keep up with what Eagle is doing these days, because I don't need it anymore. 3 PB, PB4, PB5, PB6, PB7, PB8. There we go. So these are added. Yeah, or Emacs key bindings. Yeah, having an edit and command modes, like with escape, that would be funny. Yes, 1, 2, 3, 4, 8. Yes, thanks. Yeah. It is weird doing this on stream. Somehow, because I'm commenting all the time, it is a very different experience doing this, where you have to speak over what you're doing. It's much more difficult than just sitting there and being able to focus on the thing you're doing. And this kind of mistakes where you just miscount stuff, I think I would blame it on the fact that it's not a normal environment that I'm used to doing this kind of stuff. Yeah, off by 1 hours, for sure, yeah. How do you prevent that? Okay. Left. And so crystal in. Yeah, we could actually wire it in directly into the ports. Whatever. Let's just, for now, copy the original as much as possible. Crystal in. Then we have DP for USB, DP, and DM. And I think it is L, like place wire, P. Not using shortcuts for this kind of stuff. That's just weird. I thought I was using more shortcuts for this kind of stuff, but I obviously don't. I have more muscle memory in the PCB layout probably, because you spend more time at the end in the PCB layout than the schematic capture. So yeah, that might be the excuse there. All right, so what do we need? We need 2.7 kilo ohm resistor for the I2C, and the I2C interface is used for the boot up, and it will be connected to the EEPROM. Okay, so value will be 2K7, and then let's zoom in. Move. Yeah, we need to reorganize those labels. It would be, yeah, this is the situation where you want the to enable the finer grid to get the labels tighter. Yeah, and edit and have it align right. There we go. Now we can switch over to the cursor grid, because this now we are moving the component. Okay, so we also need the label here. We need to call it SCL and SDA. Let's do that. SCL SDA. Move. Okay. Horizontal wire. There we go. Let's make a copy. Okay, then we want these to be pulled up. So let's add a pull up here. And there we go. 3v3. There we go. So that's done. Next, we will add some resistors to make sure that the reset and wake up are in the correct state. So the reset pin, according to the old schematic, has a 2.7 kilo ohm resistor as a pull-up, and it has 1 microfarad capacitor for smoothing so that it doesn't bounce around. Okay, so let's do that. We can also call these signals. I'm not sure we will be using them, but let's just do that, and this will be tilde reset. Tilde makes a bar on top. That's very convenient as a negation, because it is not reset. Then we have wake up. All right, and let's copy the resistor and move it, and then copy. The wake up resistor pull up is F100K. 100K. Pull up. Now wake up is overlapping, so let's move this. Make some space, and then move the trace. There we go. Okay. Now we need to add some more stuff. And that would be 3.3 volts pull up plus its capacitor. Yeah, how to make it nice? Well, let's just put it here for now. There, and then we have the capacitor. Move this here. Yeah, just to indicate this is just connected to power here. Let's do this, and do this, and pull it down to ground. Okay, so let's add a new power symbol. That will be the ground power symbol, GND. Very nice, done. I can move it up. There we go. So that's nice and clean. Now, what is with the reserved pin? The reserved pin has to be pulled down to ground according to Uwe. That's probably somewhere in the data sheet or in the reference manual. So let's do that. And then let's add a label as we had on the previous schematic. Yeah, I'm curious what this does. Probably it is some hardware debug thing, and it if you pull it high, you get access to some goodies. Someone should try it out. Okay, so this is all ground, analog ground, and normal ground. So let's connect this up. And copy. There we go. So now we have ground connected. Oh, and that would be it. We have it wired up. Very nice. Okay, so that is the FX2 chip. Now let's get also the LED connected, because that caught my eye first. It was a separate schematic or separate like block on the old schematic, but we can add it here. First of all, we need to add an LED symbol, device, LED. There we go. Yeah, let's just wire it up here, just to be different. Yeah, so that goes, and this is connected to ground, but it is connected through a resistor to ground, because we need to avoid the LED just from burning up. So we need to do current control on this. So let's put an LED. What did Uwe use there? He used a 2.7K. I think he likes the 2.7Ks for stuff. That's fine. There we go. So that's connected, and let's connect it to ground. Just copy and done. So that LED is connected now too. Yeah, let me check if there's anything here. Nope. Okay. All right. So next, let's add the circuitry for the USB connector. Why not? That's a good idea, probably. Then we need VCC. This will be 5-volt power. So let's add the power symbol for that. We will need to take the 5 volts and then step it down to 3.3 volts for the microcontroller, but that is a separate part of the circuitry. 5 volts. There we go. 5 volts. Bam. And yeah, let's add a secondary label too, just VBus. There we go. Now we have D+, D-, and ID. ID we are not doing anything with. We leave it unconnected. So let's mark that as such. Then we have D+ and D-, D- and D+, and then we have ground. Let's do this like that. This is connected to the case. So this is the shield connection. We probably will change how it is wired up, because shield should normally be connected through through some resistor or some other stuff, because it is there to do shielding and not run power over. It's usually a good practice. To be honest, I never do that. I pretty much in every design I just connect the shield to the ground pin, as many others do. Yeah, ferrite beat to radios noise, that's exactly right. And I've seen also some capacitors on it and stuff like that. So just to smooth it out, still have it connected, but not directly to the ground of the target device. So you would, for example, if the target device would have a lot of noise on the ground plane, it probably would start just spewing it out through the shield of the USB cable. It's probably not a good idea. So let's copy this, another ground, and then we can connect it to DP. Yeah, why? Why are we doing this? This is dumb. Let's just move this over. No, it is actually not dumb, because they're in reverse. The D+ is on the bottom and D- is on the top. Okay, fine. I will use labels instead. Silly. Okay. DM. Rotate this, and then D+. Yes, D+. Also rotate. All right, so we have the USB connection connected. That's nice. What next? maybe we should add the voltage regulator. That's probably a good idea. The voltage regulator will take the 5 volts and step it down to 3.3. Let's add a symbol for my favorite linear voltage regulator in an SOT5 or SOT235 package that I use a lot. So VREG 5-pin fixed. There we go. And that's the doodad. Let's edit the value. It will be 3.3 volts. Let's call it that. But usually I should actually have the name of the, in the schematic here it says Micrel 5504, so MIC 5504. So for this part I could actually use a specific part number. I could look it up, but I'm too lazy now. I have a different part, not from Micrel. Micrel is nice. It is really low noise and low dropout, but they are quite more expensive than I think it is worth it for this kind of a design we have here. So we will use something else. All right, let's wire it up. So VBus will go in here, and then it's like we have now 2 labels for that net. It's like one name for that net is plus 5 volts, and the other name for that net is VBus. I think we should just call it one thing and decrease the amount of confusion. So let's do this way. Remove the junction and then wire to 5 volts. Okay, so then we have 5 volts here, and this will be connected to a decoupling capacitor that I should look up in some other, because I could just copy what is on here, but I could also use the correct schematic based on the datasheet of the part that I will be using. And I know for a fact it is a little bit different than this. So maybe we should just look it up really quick. So I will save this. This is the nice thing file. Open recent. Let's open the Blackmagic probe design, because I know that the schematic here uses the layout that I want. So let me just make a copy of this really quick. So this will be a 4.7 micron the input, 7.4 large on the input. Then the bypass capacitor, I use that just to decrease noise on the Blackmagic probe. I'm not sure it is really necessary, but it doesn't hurt. And this is 10 nano. And then on the output we have a 4.7 micro again. It's the same capacitor. And these are 0603s, these two, because at this size, it's like 4.7 micro in an 0402. They get quite expensive, and there is not really a reason besides just my anxiety of size, I think, to make these really 0402s. It's like I think I can handle a few 0603s on the board. Yeah, FCC emissions. Who talks to FCC? Do you? Okay, so let's open the schematic. There we go. Yeah, it's like I'm lucky that most of the stuff that I make are development tools and evaluation boards. Basically, it's subsystems. So I basically say it's like someone else deal with FCC. Okay, so there we go. Consumer products are a pain, and dealing with FCC from that perspective, it's a pain. I did deal with TUV in Germany to do the certification, and it's no fun. You have to always find all the loopholes you can to get your product past all the certifications, especially when it's like a medical device, for example. Anyways, side story. All right, so we said we want a 4.7 micro over here, but to indicate that it is an 0603, we will just use the symbol of the large capacitor, because we don't have many of them and we don't have many different sizes. We have 0603s on this and over 02s, so I will use just two symbols to make it easier to read the schematic. Okay, so where is it? Capacitor, normal size, and that would be the 4.7 micro for U7. And we have to copy this guy. Oh, we could edit this and actually set the value of this one. This is 1 microfarad. We can either use an 0402 or an 0603. Yeah, I have to check. I think I used most, or what do I have on the pick and place machine? Because that would be nice to reuse the same setup. I think I have 0402s in 1 micro, but I would have to check. This is something to check later. 1U, okay, 1U. And then let's copy it over, but also change the value of this to 10 nano. 10 nano, yes, there we go. And that would be for the bypass capacitor. Let's move it. I think we need more space here. Move. There we go. There. So we have the 4.7 and the 10 nano. Let's copy it to the output. And then we can connect this to ground. Just to make it pretty, we will put it on the same level. Copy this. And then bam, 1.7. And then yeah, let's move this like this. And there. Okay. Now I said I wanted it pretty and I did it ugly. So let's move this. All right. Now we have to add these two, and this will be 5 volts. And 3.3 volts. There we go. Done. And enable has to be connected to 5 volts. That's what we forgot. There you go. Yeah, I did this. Or to the top. Yeah. It looks weird. Junction. No. Delete. Let's do this like that. Does it look better? I think it does. I could also just wire it here directly and then... Anyways, this is really being anal about this. All right. Power supply. Done. Next, what do we need? We need bypass capacitors for the power supplies. There is 600 nanofarad bypass capacitors for VCC input. They probably should be very close to the VCC pins here on top. So how do we do this so that it is nice and clear? Uwe put it in the corner here of the schematic, but I think I will put it on the top here just to have it closer to those pins, just to indicate that this is what we need. Okay, so let's copy the capacitor here. And this will be 100 nano. nano, copy, and we need 6 of them. No, not field value. I don't want to copy the field value. I want to copy the component. Let's move this down. Yeah, let's put it on the left, like this. And copy ground. Copy ground, good. So we have 100 nanos. Let's add the label, the 100 nano bypass capacitors. Okay, so let's add the legend. And that would be 100 N bypass caps for all VCC pins. There we go. Let's add it here. And now let's copy this guy. And then for the VCC pins, this is the analog VCC pins, we use 2.2 microfarad and 2 100 nano. Okay, so 2 100 nanos and then 2.2. So 2U2 for 2.2 and then 2U2. There you go. So that's for the analog stuff, analog domain. All right, 3.3 and ground. Copy. Go. And let's add a legend for this. And this would be 2U2 slash 100 nano bypass caps for all AVCC pins. There we go. Perfect. Very good. Okay, so we have the bypass capacitors. Very nice. What is missing? We are only missing the crystal for the system clock and the connector from the old schematic. Let's save that just in case KiCad decides to quit on us. And let's do the crystal. Okay, so the crystal is, it's a device, and we have an XTAL XGX. No, it's an XGXG, so it is crystal, ground, crystal, ground. The XGXG stands basically for the pad assignment, in which order they are. It's a convention from the KiCad libraries, that they some symbols basically have the numbering of the pins so that the pads are being assigned correctly, and you use the footprint in multiple devices. So you have the symbols have different assignment of the pins so that you know which pads will end up with which pins. It's how KiCad does it. All right, so we have ground and we have, it's add a value to it, and it will be a 24 megahertz crystal, and H is obviously large. Okay, so that's 24 megahertz. We need input and output, and we need the special capacitors here too, and they will have 12 picofarad. I have to check what value the crystal is that I use. I think it needs 10 pico capacitors. But yeah, let's just copy it for now from what it is. But I should add a note to the schematic that this needs to be checked so that I don't forget later. So let's add the ground first. Ground, copy, and another ground. This is ugly. Okay, let's copy this. Yeah, one thing, never turn around your ground and power labels upside down. It is really confusing if you do this. Please don't do that, whoever does these kind of things. Ground always point south and power, like supply labels, point north. Thank you. All right. So this is crystal out and crystal in. I don't think it matters, especially when the crystals are symmetric. It matters for the chip, which one is which. If we were inputting just this outside reference signal, like a square wave, for example, or a clock from a different chip to get everything synchronized on the same clock, you would only insert the signal into extal in input, but we don't need this here. Just a side note, because I thought about it. There we go, and we need the capacitors. And they are 12 pico, I think. 12 pico. 12p and 12p. 12p. Very nice. So we have that. Let's make it symmetric so that it looks nicer. There we go. And then get the ground connected. We'll get a sip of water. All right. There we go, and there we go. Yeah, let's add the labels, and we need extal out. Yeah, I can also copy them. So copy them. Come on. Copy, I said. And copy this one. There we go. So that's connected. So we have crystal now. Very good. So we have an external clock. What else? We should add at least a mock-up of what the probe input will be. So let's add a symbol for that. So this is an exception for what I said before. This is something I do use from the standard libraries. It is connector symbols. Yeah, so hypocrisy, yay. 5, so it is a 2x5 connector for now. We can always change that later, and just to have something so that I have the old schematic copied with new settings from KiCad, so that the old defaults are the new defaults, because the schematic, as I said, was made such a long time ago that it is using some old KiCad defaults, and it would be nice to start from scratch and not pull legacy with you. Like probably Chris Pivina will bash his head and scream when he sees that, but I'm sorry, I apologize. Okay, so let's add the connection. So Uwe decided to have, or it is based on some other designs that use also an 8-pin connector or 10-pin connector. It's like to have these two be ground, and then have the signals be available on these here. Okay, so it's a staggered input. Yeah, 1, 2, 3, 4, 5, 6, and so on. So we will follow that. Let me copy the ground connection and copy, copy. And let's add labels. We will start making the modifications after we are done with this. So write PB0, PB1. Let's see if I can count this time. PB1, PB3, PB5, PB7, PB, caps lock is also useful, PB2, and PB4, PB6. There we go. Do we have it right? 0, 1, 2, 3, 4, 5, 6, 7. I can count. I win. All right. So now I think we have everything. Everything that was in the old schematic is also in the new schematic. What the old schematic also had some footprints already assigned to stuff. So let's just do that. So the big ones, we should assign a footprint here and use the 0603 footprint and disable showing because we don't need it. Then have this also assign footprint 0603. So this is a funny side note. KiCad, if you run it on macOS, for example, does not have the browser. You have to like type in and search this stuff. It's really annoying. I don't know what the exact reason is for that, but it is really missing there. So the browser is for some reason disabled or whatever, at least in the nightly builds, but I can check again if someone wants to. But I think it is the case. All right, so we have a bunch of stuff from the old schematic ported over. Okay, so where were we? We were adding footprints. Okay, so we added footprints here. We should have footprints for all the 0402s. Yeah, so what we could do is just go to CVPCB. This will require us to annotate all the symbols so that they get numbers annotated. Let's do that. So now it doesn't say C question mark anymore after we are done with this, unless it crashes. Hello? No, it just took forever to load. All right, so it assigned the numbers, so it is C1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, instead of having a question mark after the letter designator of what type of a part it is. So for the LED, we will also use dipole 0603, and no, not C0603. We have a specific footprint for that. This is an LED 0603. There we go. The Cypress chip is that I did that the other day. I created the necessary footprint. It's a 56 QFN 8x8 millimeter with a pitch of the pins of 0.5 millimeter. So we add that. Then we have the connector, and let's just use for now the standard JTAG connector, namely the 10-pin 0.05 inch pitch connector, because that's what I want to do. Yeah, some people might scream now, but that's what it is. USB, where is it? I have it in Samtec. There we go. Samtec footprint FTSH 05, then the USB OTG, should be in connectors, USB-A SMD. No, not USB-A. What are you talking about? We want the connector USB micro. There we go. The 3.3 voltage regulator, it's an SOT, as I said, SOT235. And the crystal is, I think in MISC, it's an ABM8. So it's a Abracon, I think, part. It's a footprint. This is something we have to check. All right, save and exit. So this should assign all the footprints into here, into here. So now, what do we do next? We should probably consider the changes and additions from for this design that we want to add additionally. And let's see. Nano footprints. Right. I said we should leave a note to check the capacitors. So let's add that. Check. Let's leave a note here. Check Xtel cap values. That's one. There was something else I had to check, I think, but I don't remember. All right, so let's save this. And the next thing we want to add is the input protection for the inputs here. So a solution to that would be to add 2 resistor arrays that add like 100 ohm resistance, just to protect them a little bit from overcurrent. So let's do that. I will use a good and trusty resistor array symbol. So device, it's a 4 up resistor. So it has basically 4 items inside, and each of those units represents a part of a footprint. So if I set the footprint of this, you will see that this is a 4 up convex or concave. Yeah, this is convex type of an array in an 0402 package. So this is basically each element is similar to an 0201 part, if I'm not mistaken, and but you don't have to handle 0201 parts. So you have this larger part that is equivalent size to an 0603 that you solder on the board, that basically consists of 4 0201s. So let's use that. Okay, and let's add this. So let's edit and not show this. And right. So value should be just 100 ohm. So 100E. That's a European notation for just a pure 100 ohm resistor, or 50 ohm would be 50E, and so on and so forth, or 1E would be 1 ohm. So this is that, and let's copy. How do we get the labels out of the way so that we don't overlap them? Because I don't like having them all overlapping. So first of all, I want to use this and rename this to external. Basically prefix it with X. And yeah, so X. So basically we will have here on the left, we will have the internal part, So sometimes you want to label while you go down the chain. So how I do it is if I need 3 nets on a signal that goes through several stages, then I would use I prefix, then no prefix, and then X prefix. It's just the way I do it. I'm pretty sure there is some convention for that I don't know yet. So feel free to fill me in if you know one of those. All right, so let's do this. Where were we? Let's change the grid. 50. Move. That's annoying. I cannot rotate. So this is another inconsistency in KiCad. It's if you move a part and then use R to rotate it. For labels, it only goes between 90 and 90 degrees. It doesn't rotate all 360 degrees. But if you have a part and you do E, you can rotate it 360 degrees. It's really weird how it does that. So this is another one of the KiCad quirks. So what you have to then do is go align right instead and then move it and rotate it. It might be fixed in the nightly builds. I'm not saying it is not. It's just something I saw and it's weird. Yay for KiCad quirks. All right. We need 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. And let's do annotate. Let's annotate it. And then it should be R6 A, B, C, D and R7 A, B, C, D. So these are basically 2 parts with separate elements. So we have it aligned. I'm not connecting it directly to PB0 because there will be, well, actually I could, but there will be also ESD protection diodes and overvoltage clamping diodes in between that we will work on next. So let me just add the wires here. Wires at W. And let's add those. Come on. PB0, copy. What happened here? Oh, I rotated it instead of copying. There we go. Go back. Copy. Copy. Oh, and I didn't finish adding the X's, of course. X. And X. And X. There we go. Copy. Done. Copy. Rotate. Copy, copy, no, copy I said, rotate, copy, and copy, rotate, copy, done. All right, so that's done. So the next thing will be, we should have it aligned here. Oh, and I didn't switch the grid back. Yeah, there we go. So if I zoom out, I will see the secondary grid, so I can have it aligned. And this is 1, 2. So let's see if this, if I switch back, if it was, yeah, there we go. Okay, lovely. I survived. Okay, so the interesting next thing will be, if I switch here really quickly to the browser, I already looked up TVS diode. So transient voltage diode. I did use a very similar device in the past with just 2 channels, also from ST. They work pretty well. With 2 channels, this is what you need for connecting a USB. So this is for USB input protection. You have just 2 connections on this. So this is the part that we will be using. And we will have to make a symbol for this because I don't think I have one yet. Yeah, so this is the, so what it has a Zener diode for like it will reverse collapse, and then you have clamping diodes that will connect to VCC and ground. So it's basically a set of 4 clamping diode organizations and a Zener. At least this, yeah, should be a Zener diode. All right. So what we want is just to show you what I used in the past for the USB protection. Oh, apropos, we could actually add also input protection on the USB connector using the chip that I used in the past. We might do that. So let me see, where do I have it? It's in MISC or... Ooh la la. I think it will be faster if I just look into the schematic of the Blackmagic probe. Open recent Blackmagic probe schematic. Yeah, so this is the symbol, and this is the USB LC 6-2. So it has 2 channels. So you have USB go in and pass through the part itself. The part that we now chose is a 4-channel part, so it doesn't pass through the signal through the part itself. You only connect it to the pin. And so you have 4 of them in one package. Okay. Let me see if I test it, which library. Oh yeah, it is in PKL-MISC, the symbol. And the symbol is called USB-LC 6.2. All right. File, open recent. Yeah, I still feel that I have to spend some time and clean up my libraries nicely. It's like do some janitorial work on there. So yeah, let's just add it for the USB connection, just for the heck of it. PKL-MISC, and this is the USB-LC. There we go. So that would be the part. And how do we do this? So let's move the move this to here. Connect wire. Move. Although let's call it XDP and copy, edit XDM. All right. Just so that when we lay out the board, it is a little bit easier to look at, easier on the eyes. Okay, so ground. Did I connect it the right way around? Does it matter? No, it doesn't matter. It doesn't matter. It's fine. It's like when we lay out the board, we might decide to rotate the part by 180 if it is easier to route for some reason. It's like having ground and VBus in a certain position. But that's much further down the road. All right, so, and copy 5 volts, or is it 3 volts? I think it is 3 volts. Let's delete this. I think it is 3 volts. It's because the signaling on USB is 3 volts, not 5 volts, if I'm not completely mistaken. Let's save this. Let me check again. Open recent and open Blackmagic probe once again, just in case. Oh, I did connect it to 5 volts. I see. So it is actually clamped to 5 volts so that it doesn't overshoot 5 volts. Interesting. Just checking if the stream is running still and everything is good, just in case. All right, let's go on. Open recent, 2.0, schematic. All right. So it is actually 5 volts. So let's do that. This is something we have to check because I might have it wrong in the Blackmagic probe design. Who knows? What should the clamping be on the USB protection diodes? Homework. So let's just write it down just in case. Check clamping voltage. There we go. All right, so we added this just to have it. The footprint for that you can already assign to, because this is an SOT666. It's a smaller than an SOT23. So it is this guy. So if you look at this, this is the original. So this is the SOT23, and the SOT666 is basically a tiny version of that with 6 pins. All right, so we do that. Of course, disable it. I think it should be by default disabled. It shouldn't show those, but that's just me. All right, save it. So we added this here. Okay, so next thing is to make the symbol for that part. So let's go into the symbol editor. Let's open the library, that is the MISC library, and then download the original, because we will just base it on this symbol here. USB, 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 USB. There we go. Well, this is the funny thing. It's like, this is another quirk of KiCad. Look at this. Look at this. If I go on download, like get the symbol, and I scroll down, there's stuff missing. It's like I go with the mouse, look at that, go down, I'm on the uBlocks max, and then go one down. Oh, there's one part beyond that is not shown. What the hell? Oh, I love you, KiCad. All right. So we have ground V bus. What is the numbering? So let's look at the part in here. So we have pins 1. So the dot indicates pin 1, 1, 2, 3, 4, 5, 6, because usually they are counterclockwise. But let me check this. Yeah. What is the numbering? Oh, if we want it to be completely nuts, which I'm currently not, we could use the flip chip WCLSP basically. So BGA, just the die, like silicon die with the balls on the bottom. That's fun. That's something for the miniaturization exercise later down the road. Yeah, anyways, I think SOT666 is plenty. Small enough. All right. Where were we? I wanted to check the pinout of this guy, just to make sure. Having a little bit more sources than just one. There's some reference schematics. They don't show the numbering, because why? Well, let's just assume that I'm right. Okay. SOT666, and we have several, 1, 2, 3, 4. So how do we lay it out? And the Zener diode. So let's try. So I have the Zener diode in the center. I have one set of things here. So first of all, we have to go onto a much smaller grid so that we can draw on this thing. We can disconnect. Oh, wait a second. Wait a second. Let's duplicate this. Let's call it the correct thing. It is the DSILC 6-4. DSILC 6-4. So standing for 4 channels. Okay. Now we have IO1, then this will be IO2, no, IO4. So IO1, IO2, IO3, IO4. So IO1, IO2, IO3, and IO4. And now IO1 we can keep connected as it is. We move the circle here. No, not edit. Delete. Delete the circle, because this will be connected here. Delete the line. What is the width of those lines? Because I never remember. Polyline is width 0? Really? Okay. Polyline. Let's connect it here. So next we need also to get this copied. Copy. That should fit in here, doesn't it? Yeah, very nice. So we can just have it hover in here. Yeah, I'm looking forward to have the GAL interfaces on here. Pin. No, not the pin. Drag. Grab. Polyline 2 points. Grab. Polyline 3 points. Oh, and I moved it. Ah, damn. Okay. Copy block, that's what you need. Copy block. And then what? This. Move. No. Move. Polyline. Yeah, now it is doubled, but it is all over itself. That's where we want it. Move. Polyline. There. Move. Polyline. There. Move. Polyline. There. Now grab polyline 3 points, connect it. Now we can, oh, what's going on? There we go. Move circle center. Is there another one? No. So let's leave it here. So this is the IO here. Maybe we need to, so we will connect the trace in here. So maybe we can move it to the left a bit to make space so that they don't collide here. And we need also a bubble on here to make it nice and consistent. Okay, so so I have to select it again, probably. Select. Yeah, delete block, rotate lock, copy block. Problem is the copy block doesn't keep it selected. It just drops it back here. Or does it? I was wrong. There you go. I was wrong. Interesting. Okay, so I'm stupid. Move the circle and copy it here. Now, so if you select it and move it, then it will actually get copied properly. So I was wrong. That's fine. I learned something. So what we can do is try to let's try to select the other guy. Let's try to select this guy. Move it over here. right click, duplicate, copy block. Then it pastes it over there. Okay, okay, fine, fine. Good. So now I can move it over here. And let's grab it. Grab. There we go. And then let's add a polyline to here. Oh, I have to double click, double click. All right, so that's done. Now let's grab circle. Oh, I want to move the circle. Circle center. Let's move it to here. Now grab polyline 2 points. Nope. Grab polyline second 2 points. Yes. Grab polyline 2 points. Oh, interesting. What is going on here? Grab. Okay, so that's cleaned up. Now let's add in. Whoa, it's not what I meant. Okay. We have another sip. Yeah, if they don't want to collide like this and like this. Now move circle. Can we just select it, just the circle? Block. Delete, move. All right, so that's done. Now let's do that on the bottom here. So first of all, we have to delete. So how do we do this? We connect the IO2 to the top one that was before there, and then connect the 4 to the other one. It's like, it's all very cosmetic because it's just a symbol, but I like descriptive symbols most of the time. It's like, and it's a good exercise to show how to draw stuff. Yeah, so let's do that. The bubble can be reused. Move circle. Let's put it to the side. Let's delete this line. Let's move the bubble. Move the bubble. Move the line. Move the line. Okay, now let's create a polyline. Chuk chuk. And bam. Double click. There we go. All right. That. Then let's select this. And then copy block. Let's remove polyline here, and yeah, let's remove this polyline. Let's make new polylines. There. Whoop. There. Grab. And grab. There we go. Very nice. So now, if we select this, copy block, copy block, copy block, and add the polyline. So do we have all the bubbles in here? 3 is connected, this is connected, this is connected. So I can delete this guy and create a new trace. And there we go. Perfect. All right, so we have that symbol, and the library is pkl misc, and it's called dsilk. 6. Yep, and this glib, yes, and let's see. Let's see if we don't need to edit any text here. All right, so there's nothing special here. So the important thing is usually to commit that change, because that's what I like doing first. So let's commit the, yeah, if this fades away, thank you. So in PKL we added this symbol, lib, up, lib, PKL. There we go. Git status. Fade away, please. Thank you. Soon, now, good. So PKL misc is changed. Git diff PKL misc. So you see dsilk got added. Just to make sure I didn't miss something from upstream, so git add PKL misc. CI added dsilk 6-4 symbol push origin master. No, Esden master. Yeah, whatever. It's the same thing. Nope. Oh, I don't have the other one. Okay, it will have to wait. I will have to add the remote that I have write permission for. But you get the drill here. All right, so this, and now we can add those to the schematic. So let's add those to the schematic. And this is in PKL misc. Dsilk, there we go. So we need 2 of these because we have 8 channels. Yeah, we are a little bit running out of space here. So let's move this guy out of the way. We can compress the stuff a little bit. Move. Like this, and like this, like this. Is that good? Yeah, I think that's good. Move, and then move this guy just to have it, or on the bottom. There we go. On the bottom. Now move. Okay, let's see how I will route it here. So we will have PB0, then PB1. Ooh, that will be nasty. Let's do this separately. Let's put it underneath here and have these guys be nicely connected over here and just have them labeled over here. So I think that's a nicer way of doing this. So let's connect it here. Horizontal wire, horizontal wire. So they are basically in line like this. We can also add the footprints here, just because I thought about it. They are also SOT 666. Come on. And disable. All right, move. Okay, so ground, obviously, is to be connected to ground. Ground, ground. Then VBus. Actually, this way. And this way. Yeah, so I think, so I looked at some other schematics that people were using for their designs. They have a little bit more magic around the power supply side of things. I have to look it up for maybe next stream. and then we will see how that works. Okay, ground and 3.3 volts. Yeah, I think they have a capacitor there and some additional diodes for stuff. I think over voltage protection or something. Anyways, I have to check it out. It's like I like looking at other people's schematic designs to basically gather ideas together. It's like what makes sense I copy, what not I don't. Anyways, we are almost done for today here. I will just add this to here, and I think we will wrap it up because it's time for dinner over here. All right, so PB0, copy, and copy, and it should be actually PB1. So this is connected, and this will be protected on one side and then on the other side. How we will have this for the actual PCB layout, we can always change that later, because sometimes it makes sense to, from the layout perspective, to have the things in a different order and different assignment. But this is for later. We can do that later. So PB2, PB3, PB4. Rotate PB5, and I rotated it instead of copying it. Copy, label, and move. And I didn't copy it, I moved it. Okay, great. And I grabbed it, yes, instead of copying. There you go. Okay, fixed. 5 and 6 and 7. There we go. All right, nice. Okay, so now we have input protection also. So we went beyond what the previous schematic was, and that was my goal for today. One more thing we can do, just for the fun of it, we can export the net from here. And then, so first we need to annotate, okay. And then we can export the net, generate, and save. And then we can go to the PCB layout part, like here, and then import the net, just for the fun of it. Read current netlist, and there's something is complaining. Oh, that's for the diode. It has the capacitor and oh, because I used the wrong footprint. Oh, okay. Let me delete this. Let's go back. The LED has the wrong footprint because it is a designated. Okay. PKL LED. It's a dual, that's wrong. Dipole, diode, that would be a diode. Not L. L are inductors. That's dumb, see? It's like has a coil as a symbol in between the pads. That's an inductor. Okay, and a diode has the symbol of a diode in there. Okay, good. Okay, now let's generate. Generate, save. And import net, read current netlist. Now, no errors, hopefully. Close. Very nice. So now we have this mess of stuff on top of each other. So the interesting thing is I'm using stable version, namely the stable released version of KiCad. This one doesn't have the spread built in into GAL mode yet. So GAL mode is the OpenGL, the new mode that will be there to rule them all, whatever. It is a very good new interface, but it was, when the stable release was released, it was still missing a few features, so it doesn't have spread. The nightly builds already have spread built in, but because of that, I have to switch to the legacy canvas to spread this stuff around. So I go to default mode, I enable this weird switch here, and then I go onto global spread and place, spread all footprints, what did it say? I didn't even read the yeah, okay, this worked. So we go to F11, that should be the gal mode again. There we go. So now we have the parts. So this is what we have for now. We see the rat's nest, we see the resistors that will protect the inputs, we have the USB input protection, we have the digital 4-channel input protection twice here, and we have a bunch of capacitors, and we have the USB, and the wrong footprint. I wanted to use something else. Anyways, I will change that later. All right, so now we see how much space that takes. This is, I think the default canvas is an A4 page, so it's a little bit different format, but similar to a letter, US letter. And this is how much space we require for now. So I don't think this will be a very large board yet, but yeah. So we have the input protection. So what will happen next is we will have to add the flash chip, and probably we will have to make a symbol for that, unless we can use something that is already in the library. We will see. And then what we will do beyond that, I don't know yet, but then we can consider getting into some PCB layout stuff. All right, anyways, thank you very much for joining in for the stream, and let me know if you have any questions. I have created a channel on Gitter that you can ask questions, even if you want to talk later when the stream is over, because the YouTube chat will not be available because they switch off between the streams. On gitter.im/esden/live, you will be able to find this channel. Yeah, anyways, thank you very much for joining, and thank you for being here if you watched it. So to quote a channel that I really like, Fully Charged, if you have been, thank you for watching. Bye.